So to calculate the temperature at which the reaction becomes feasible, what we need to do first of all is work out our reaction. So in our reaction, we're taking 1 molecule of hydrogen, adding it to half molecule of oxygen, all in the gaseous form, to form 1 molecule of water in the gaseous state. We then need to work out the enthalpy change of the reaction. So the enthalpy change of the reaction equals the sum of the products enthalpy changes, take away the sum of the enthalpy changes of the reactants, and for this case it's going to be minus 242 kilojoules per mole for the water being formed in the gaseous state. Take away our two reactants, both of them are going to be 0 and 0 because they're both elements, and that finally gives us minus 242 kilojoules per mole. So there we go, we've now worked our enthalpy change of the reaction. The second change is to work out the entropy change. So the entropy change is given to us by the sum of the entropies of the products, take away the entropy of the reactants. So as products, take away the entropy change of the reactants. Well, in the products we have only water, so that's 189, and we then have two reactants. We've got 1 molecule of hydrogen gas, 131, and then we have a half a molecule of oxygen gas, so it's going to be a half times by 205. If we then carry that on, we then get 189, take away, keep the brackets for the time being, 131 plus 102.5. We can then add this together to give us 109, take away 233.5. And finally, we can then take one away from the other, and we end up with minus 44.5 joules per Kelvin per mole. So there we have it. We have first of all our entropy change. So we've got our enthalpy change, then we've got our entropy change. We could then look at the Gibbs free energy. So our third calculation, our final calculation, is to work out the entropy, the Gibbs free energy. So the Gibbs free energy is given to us by the formula delta G equals delta H minus T delta S. And delta S here really is for the entropy change of the system. So we're going to assume that delta G is 0, because it has to be less than or equal to 0, because of minus 242. We've got times by 1,000, because our value is in kilojoules per mole, we want it in joules. Take away minus T times by, we're then going to multiply that by the entropy change. Now we need to have that all in brackets, so minus 44.5. If I then next look at doing the doing the multiplication, what we can do next is 0. And that equals minus 242,000. And the two signs, the two minuses times together to give you a plus, and that ends up with 44.5 T. Okay, so if I can do the following, if I now rearrange the formula, I can say that 45.5 T equals 242,000. So I've basically taken the T to the other side and multiplied everything by minus 1. If I now divide by 44.5 on both sides, I end up with the value for T. So to finish off, I get the value of 242,000. And if I put this into my calculator, so 242,000 divided by 44.5, and I get the value 5,438. So I can put that down as my final answer. T equals 5,438 Kelvin. Okay, so where are the marks in this question? Remember, it's a 4-mark question. The first mark is to work out the enthalpy change of the reaction. The second mark is to work out the entropy change, delta S, of the system. The third mark is for stating delta G equals delta H minus T delta S system. And finally, the fourth mark is for working out the final temperature change.